I'm Anil Kumar. I'm a technical product manager at Couchbase. Today, in this session, I'll be talking about how to keep your sensitive data safe in Couchbase using Gazang. So I'll start with a bit of introduction to the Couchbase server, and I'll go into the Couchbase architecture, and I'll explain how the right operation happens in Couchbase server and the persisting to the disk. Then I'll talk about some of the security features we currently provide in Couchbase. And we will go into the topic of what solution Couchbase provides in terms of encrypting your data on disk at rest. So as most of you already might know, Couchbase is a NoSQL document database. It's for interactive web and mobile applications. Couchbase is the company behind the Couchbase open source project, which is one of the leading NoSQL database projects, which is focused on a distributed database technology and all the surrounding ecosystem around it. We support both the key value use cases and the document-oriented use cases. Right? So the Couchbase open source project itself is completely open source under the Apache 2.0 public license. All its components, including the Couchbase SDKs, are all open source. You can so you can download the Couchbase in two editions. We have Enterprise Edition and Community Edition. You can find both the you can download the Couchbase from our website at couchbase.com/download, and they are free to download. So you can, in terms of features, both the Enterprise and Community Edition comes with the same features. Just to give you an overall overview of some of the core principles of Couchbase Server. So we have easy scalability. What this means is you can easily grow your cluster. You can add multiple servers to your cluster. You can remove multiple servers from your cluster just by a click of a button, and without affecting your application. Consistent high performance. With Couchbase Server, we also support memcached, which is in-memory object cache, with which we can provide a sub-millisecond response time for any read and write operations. So when I explain the Couchbase architecture, I will go into the details of how we have this, how we provide the in-memory object cache, and how we achieve the sub-millisecond response time. Always on 24/365. What this means is all our operations, all our maintenance operations are all online operations. If you so any rebalance operations, compaction operations are all online. So your application will never see a downtime. Flexible data model. We support JSON natively in Couchbase Server, including our Couchbase SDKs also support JSON natively. So now you get flexible, you get the schema flexibility. You can store JSON documents in Couchbase Server. So now let's look at the Couchbase architecture. And this is really important because so once we understand what the architecture looks like, then we can it will be easy to understand when we persist the data to the disk, what happens and how the security features work on top of the Couchbase Server. So the architecture of Couchbase Server. So we have so in one important thing to mention here is Couchbase Server. We don't have the master-slave architecture. So in Couchbase, all the servers are identical. So if we have a 10-node cluster in Couchbase, all the nodes will be identical. So we have a share nothing architecture, and this is important because we don't have a single point of failure, and this is how we achieve our easy scalability. You can add multiple servers to the cluster and expand your cluster. So we have two parts. We have a data manager part and the cluster manager. Data manager is written in C and C++ for high performance. Cluster manager is written in Erlang, which is one of the best optimized for the cluster level activities. The data manager, as you might guess, it is responsible for all the data related operations. It has three components. It has the in-memory object cache, it has the persistent engine, and then it has the query engine. Whereas the cluster manager, which is responsible for all the cluster level activities, such as rebalance operations, failover, all this are taken care by the cluster manager. Now let's look at some of the operations in terms of how you persist the data to the disk, to the Couchbase server. So at any one point of time, the application server will be talking to only single node in Couchbase. and this is how we guarantee the strong consistency. If in case if the server goes down, the replica partitions on the other servers will be activated and they will start taking traffic. So it's at any one point of time, the application server will be always talking to the active partitions in the Couchbase server. So here let's look at the write operation. The application server tries to write the document to the Couchbase server. The document gets written to the object cache, the in-memory object cache, and to provide high durability and the availability within the cluster, we write to the two queues. We write to the replication queue and the disk queue. The replication queue is for sending the data as quickly as possible to the other server, so that in case if the server goes down, we have the data backed up in somewhere else. Whereas for the persistence, we write the same document to the disk queue, which gets written to the disk eventually. And one of the optimization we have added in the disk queue is we do the dedupe. In the sense, if the same document gets updated multiple times within few time frame, few seconds, for example, so we don't write all the changes to the disk. So we do the dedupe. We write only the latest and greatest document to the disk. So now let's look at the how update operation happens. If the same key gets updated, so the document gets in memory we do the in-place replacement, right? And again it gets written to the replication queue and disk queue. But now when it gets persisted to the disk, it's not the in-place replacement. It's not the in-place replacement on the disk. It's the append only structure. So what this means is we don't for the high performance when we persist to the disk, we write to the end of the file. And we have an online compaction job which goes and deletes the old data from the disk. So now that we have looked at how the write operations and update operations happens, to just give you an idea of how the read operation happens, since we have the in-memory object cache and it maintains the active data set, so that's how we guarantee a sub-millisecond response time. So if the request comes for the document and if the document is in the memory, we send the response as quickly as possible. And most of our use cases, for example, ad targeting use cases, where they require a sub-millisecond response time, we guarantee the sub-millisecond response time using our in-memory object cache. Let's say that your application starts growing and you start writing a lot of documents to your Couchbase server. At some point, there will be no room for new documents. So we evict some of the documents from the memory. However, those documents are already persisted to the disk. And the eviction happens using a algorithm which is not recently used algorithm. We pick only the documents which have been not used for certain period of time, and only those documents will get evicted from the memory. So in this case, because the document 1 doesn't exist in the memory, it has to be fetched from the disk, and that operation does have the latency because it has to be fetched from the disk. So that's why we kind of maintain the active data set. When we size your cluster, we make sure that the memory quota is properly allocated. So moving on to some of the security features we provide in Couchbase Server. So in Couchbase, bucket is equivalent to a database. So we can create for your application, you can create a single bucket or you can create multiple buckets. And this bucket is equivalent to a database. We have two ways to create a bucket. In general, by default, it creates a bucket without any authentication, but you have another way of securing your bucket using the SSL authentication. So your client, when it needs to talk to the server, it has to do the SSL authentication. And in our last release, we added the crime MD5 encryption for the authentication. So the client to server authentication now happens on the crime MD5. So when you in the initial phase, when you try to create a bucket in Couchbase Server, it will prompt you with the access control, and it will ask you for the password, and this will happen on the port 11211. Now, in terms of providing the encryption of data on the disk at rest, so we have a solution with the Gazang. The Gazang is very well optimized for for encrypting the data on disk, right? And Robert Linden from Gazang, he's going to do the deep dive into the zNcrypt technology, which does the encryption for Couchbase. We have a connectors page on our Couchbase, which talks about. I can quickly switch over to the page, which talks about the Gazang, and we have a data sheet, and we have some the use case information as well as the high-level architecture diagram here. So I'll pass this to Robert, who will now explain about Gazang and the whole zNcrypt technology.
Thank you, Anil. Let me switch the screen to Robert so he can go into details about the Gazang solution.
Great. Yeah, thank you. And let me share my main screen here. All right. Is that coming up for you guys?
Yes, perfect.
Great. All right, let me put this in presentation mode. Okay, great. I really appreciate everybody taking time to hear a little bit more today about Couchbase and then how we can help secure any sensitive data you may have in your Couchbase environment using Gazang's data at rest encryption and key management. So what I'm going to do today is first just a brief overview about Gazang, about our company and what we do, and then we will get into a pretty technical dive into our encryption and key management solutions, and specifically about how they will work within a Couchbase environment. So, and again, my name is Robert Linden. As I was introduced, I'm a senior solutions architect or systems engineer here at Gazang. I've been here for almost 3 years now, and am looking forward to going over all this with you. As you have questions, I'll repeat again too, please put them into the chat window, and we'll try to take care of as many of those as we can towards the end of the presentation. Gazang is headquartered in Austin, Texas. If you that tall building there on the left side of the picture is actually where our corporate headquarters is, right to the left of that Texas flag. And Gazang has been around really for almost 4 years now, and our focus has always been on security, specifically around Linux and open source. And today, with the gaining popularity of fantastic big data and NoSQL type databases like Couchbase, that has been our primary focus. I will go through how we handle data at rest encryption and the key management, as I said, and really any type of use case you have in securing cloud and big data environments. That's really what our specialty is, and how we're helping the majority of our customers. You can look along the bottom here. This is just a few of our existing customers. Key verticals, as you can see here, financial services is a very common use case for our customers. Healthcare is huge for us and for our customers, and of course other retail, government, education, and technology. The particular vertical really does not have a big impact on us. We can really take care of most of those use cases very effectively, and you'll see why that is when we get into our technology. A couple quick examples. 3M Health Information Systems is using a big data deployment where they have a special dental scanning solution, and they're able to, we're helping them secure all of that patient data and other information in there with our high performance data at rest encryption. And one of the main reasons they really looked at Gazang was the way we're able to transparently encrypt the data, meaning no impact to their infrastructure that they had already built and worked on. And I'll show you how that's exactly what we can do for you in your Couchbase environment. Another interesting example is Insure. This is the state of Minnesota, and they recently put up their new healthcare exchange as part of the new healthcare laws here in the United States. And this was an extremely time-sensitive project, and we were able to roll this out with the state of Minnesota, and the consultants that were working on this literally have their entire environment encrypted and ready to go. Our part of it was done in less than a day. So we're able to very easily deploy, scale very easily, and again, I'll touch on those as we go through. So it's just a couple of examples of what we've been doing in the marketplace. Those customers just listed and our over 250 other customers that we currently have, we hear very common problems and common questions is, I need to protect sensitive data in the cloud, or really anything on Linux is what we're able to do. So whether it's on-site or in your hosting provider, that's really what our expertise is, the ability to come in, lock that data down with data at rest encryption, but also with key management. And that, no pun intended, is really key to a good encryption solution, and you'll see that in just a minute. So whatever your driver is, the reason you need to protect the data, if you've got medical information, and HIPAA is a requirement to protect that, payment card industry requirements and regulations, student data, any of those verticals we mentioned, we're able to, again, help you secure that. And even if it's just personally identifiable information, you want to be sure that your customers' emails and phone numbers, for example, don't get out to a competitor or to something like that. We are able to help secure that. Big data is a perfect fit for us. We're positioned perfectly as this wave has been coming through to help customers all over the place secure their Couchbase databases and really lock this down, but still maintaining very good performance. And I'll talk about that in just a second as well. Another thing we hear from our customers is we need to control keys and other security objects. So we have a separate key manager, as you're going to see, to secure the encryption key that controls access to the secure data with our data at rest encryption. But customers wanted also, if they had the opportunity, to secure other objects, maybe SSL certificates for websites, other non-Gazang encryption keys, even secure passwords and other security objects for critical systems. Well, our key manager can do that as well. I will not be spending a lot of time on that today, but just pointing out that that is another use case we can potentially help you with in addition to securing your Couchbase data. And finally, as I said, we're a security company, and everywhere we can, we try to implement security best practices, multiple layers of authentication and security, keys, encrypting keys, while still maintaining a good performing platform. That's really what our focus is all the time, and hopefully you'll see that today as we go through. So enough about Gazang and our background. Let's look at the technology and how we actually do this. So in this diagram here, what this represents is a Linux node running Couchbase data. So as you can see, the Couchbase application itself sitting on the server. And the area where we really focus is right around the Linux file system itself. So I've mentioned a couple of times we are a data at rest encryption for the Linux file system. Here we sit right between that Linux file system, whether you're running ext3 or 4, or you want to take advantage of what Gluster or Riser file system can offer you in your Linux environment. Our encryption really doesn't care what that underlying file system is, as long as it's a compatible Linux version that we support, which you can see on our website. We sit right between that file system and then the Couchbase database, or really any application or service running on Linux, we can help secure in the way that I'm going to describe for you here. So in the example of Couchbase, let's say the way our encryption works is we can target any file or directory on the Linux system. So this box I'm drawing here, let's say, represents the data directory for the Couchbase data for this particular node. So I think that's in somewhere like opt Couchbase, and then there's a few more paths to this data directory, but that's going to be the target of my encryption. When that happens, the command to encrypt that Couchbase sensitive data on this system is actually called zNcrypt move. I don't think I mentioned this. zNcrypt is the name of our data at rest encryption solution. So zNcrypt move is what I would execute against that Couchbase directory. And what will happen physically under the covers here is we will literally move all of that data out of the original Couchbase folder that it started in into some folder that you've designated as your encrypted file store. Let's say we want to put it in var lib zNcrypt storage. So that's where I want my encrypted file system to live. So we will physically relocate that Couchbase data into this new directory, And now it lives over here. And then in what we call a virtual encrypted file system, this is a layer that we virtually put right on top of the native Linux file system. We also create a mount point. So let's say this is var-lib zEncrypt virtual. So virtual and storage are associated together as part of the configuration of our zEncrypt client. And this virtual mount point directory becomes a symbolic link that replaces the original directory location. So I've moved all of the sensitive data into the storage folder, and I've replaced the original data with a symlink now that is associated through the zEncrypt client into the storage directory. So what happens now is we then set up our access control layer that allows or disallows certain access to the sensitive files in the Couchbase database. So here in the case of the Couchbase server, I set up the appropriate trusted processes. Everything that Couchbase uses to read and write to this file system, or to the data that it uses, which is now in our encrypted file system, those are set up as trusted processes. And actually, in the case of Couchbase, there were 3 different processes or executables that I had to define, which you'll see in the demonstration in just a minute. So there were 3 process-based ACL rules that enable Couchbase now to continue to function exactly like it did before. Because those trusted processes in the access control rules, when zEncrypt sees those processes trying to read and write to this original directory, we then use this symbolic link as our control point for that access control. So those 3 trusted processes now will always be allowed now to continue to read and write across this symbolic link into the encrypted file system. zEncrypt handles all the encrypting and decrypting of the data on the fly. As Couchbase writes new data into this directory, it is automatically encrypted. As Couchbase reads from this encrypted file system now, it will be decrypted automatically on the fly. So Couchbase doesn't even know that anything's been encrypted. We are, from this point up, from the original file system in the directory that we've set up to the trusted processes that have been defined in the ACL rules, it is 100% transparent. And what we mean by that is you do not have to make any changes in your configuration to Couchbase. So however you've optimized that application, you've got everything tweaked and designed exactly how you want it, you can implement the Gazang encryption, this data at rest encryption, and everything I've described without having to make any changes at all to the Couchbase server. And of course, that translates up a little further to the Couchbase interface, which I know runs on the same thing, or any application that you might be accessing from a website or any kind of application layer. No changes there either. So that is one thing that our customers really, really like about this Gazang zEncrypt encryption, is that it is totally transparent to the applications that are using the encrypted data. Now, so that's the first benefit of these process-based ACLs, is total transparency, 100% transparent data encryption. The second big benefit here is let's say I'm a root system administrator here, and maybe I'm not a good guy root system administrator, and I want to go dig around and find some sensitive information inside the Couchbase data directory here, and I'm going to attack it straight through the file system. So here I can go in and run concatenate across any of those the files that consist of the Couchbase database here, and list out the contents of those if they're not encrypted by running, as I said, concatenate or tail or more, or any of those type of commands. But when I have zEncrypt in place, and because of our process-based ACLs, if I have not listed concatenate as a trusted process, or more, or tail, or any other commands that might allow me to read the contents of that file, even as a root system administrator, I will get a permission denied message. And then you're going to see this in my live demonstration coming up in just a second. So the second big benefit of this process-based controls is separation of duties. I can have a root administrator that has full reign over this system, good guy or bad guy. We still may want to separate out, especially if I have sensitive health information or payment card data or whatever kind of sensitive content is in the Couchbase database. that system administrator may not have any business being in there. And with zNcrypt in place and the encryption set up the way I'm showing you here, there is no way for that administrator to directly get in and access that data. Well, the only way is to go through a trusted process that had been established in our ACL rules. And by the way, I'll show you that too. Those rules are even locked away only for Gazang administrators, and I'll show you the mechanism that allows for that. So we secure that information as well. All right. I've mentioned a couple things about performance, but I want to be a little more specific for you now. We generally see, or our customers generally see, only about 2, maybe to 5% on average overhead added because of our encryption. So if we were to benchmark 2 identical servers, one with zNcrypt, one without, consistently across the board, we see between 2 and 5%. And that's referring to CPU utilization, disk I/O, as well as latency for transactions against the database. And this is for lots of different databases. I don't know that we have specific Couchbase benchmarking right now, but I know that's something that we are currently have in the works. But generally, in every other use case, we have seen that very low single-digit performance. And it's primarily because of the on-the-fly encrypting and decrypting as data is read and written to and from the encrypted file system. Very scalable and easy to deploy. I'll touch on that a little bit if we have time. And then the last piece is the key management. And this is another critical component to any encryption that you may be looking at. And I really, I'm sure most of you know this, but you have to really consider, even more than the encryption itself. I didn't even mention this, but we're doing AES 256 encryption by default. That's considered unbreakable with today's computing power. It would take tens of thousands of years, I think, is what I understand is to brute force an AES 256 encryption. Well, you don't have to brute force it if I store my encryption keys in the same file system where I've got the encrypted data. And that's what a lot of our customers were having to do to meet the encryption requirement, but still have a functioning application that could get to that encrypted data. Well, we take care of that. We do not write the key anywhere locally on the file system, but instead hold it in the Linux key ring inside volatile memory. The key ring is something Linux has given us to manage these kinds of objects. So our key is held up here in RAM, the file level encryption key that controls access to this data. We then store a copy of that key onto zTrustee. This is our other solution used together with zNcrypt to provide the encryption and key management. And the role of zTrustee is simply to provide a seamless, unattended, but secure reloading of the key back into your encryption client. So if I were to shut this Couchbase server down, power down this node, because this key is in volatile memory, it's going to fall out and it's gone. And when this node comes back up, we have to have a way to get that key back into memory so that your server can function and Couchbase can read and write to its encrypted data. And so zTrustee provides that secure mechanism for restoring that key. And here on the next slide, I'll go into a little bit more detail on exactly how that happens, and then we'll go to our demonstration, and we'll get to see this all in action. So over here, I'm going to draw this back so it kind of connects back to the other screen here. This is all my layers of my zNcrypt client, the encrypted file system, and the trusted process, and Couchbase up here. So here's my Couchbase process that's trusted, coming down here to the data and my encrypted file system and the encryption key. All right. So this key, as I said, an encrypted copy of this key is what's stored on the zTrustee server to provide that seamless reloading of the key back to the system. And the way we do that, when I first install my zNcrypt client, I have to do what we call a register. In fact, the command you'll type in is zNcrypt register. And what that's for is establishing a secure connection here with the zTrustee server and this client. And in that connection, the primary object that is created during that registration is another encryption key. Actually, it's a pair of encryption keys, a public-private pair of GPG encryption keys. So here I told you about keys encrypting keys and multiple layers of encryption and authentication and so forth. Well, this public-private key pair, what this means is, if you're not familiar, is that One key encrypts the object that needs to be protected, and then only the other key can decrypt it. The first key is not able to decrypt it, only does the encryption. And so this provides us a more secure method of encryption and protection. And so what happens is this file level encryption key that controls access to this encrypted file system is encrypted with the public key and then stored over here on zTrustee. So here's the copy of my file level key, and I'll do this to indicate that it's been encrypted with the public-private key pair. So you can see it's obfuscated and protected. So all it is on the zTrustee server is an encrypted blob of data. Nothing here that can even be used. If someone were to run away with zTrustee under their arm, they've got nothing useful. A bunch of encrypted blobs in a Postgres database. So the reason this works is because this private key that can decrypt this blob only lives here on the server. Now this is written to disk on this server, and its job is simply to retrieve this encrypted blob of data, then decrypt it locally and load it back into memory where your Couchbase database can now read and write to the encrypted file system. And so that is how we are protecting all that. Now a question somebody is probably asking, well, what if somebody gets in and they grab my encrypted file system and they grab my private key, the copy here that can decrypt the other file key? Couldn't they go then load it all up on another server and then attach to zTrustee and be able to get my data? So the answer is yes, but only with one additional piece of information. So we're actually protecting from that type of exploit. You cannot take just the private key and the data and be able to successfully connect to zTrustee. Remember that whole registration process. One thing I haven't told you yet is there's still another encryption layer that we have. We utilize this with what we call a master key or a master passphrase. This is something that you know or that you possess a copy of. It can either be a password or an RSA key file that you have pre-created for this purpose. And this master key is your key of last resort, so to speak, for all things Gazang. You're going to see in the demonstration, as I'm about to go to next, that I have to know this master passphrase in order to do anything in Gazang. And if I were to take the private key from my public-private key pair and the data and put it down here on a new server, I could connect to zTrustee and retrieve this encryption key, but only if I knew the master passphrase that controlled all of this here. So that's our last level of security there. Again, something you know. That master passphrase is also the mechanism that separates a normal root administrator from a Gazang administrator. And you'll see this again in the demonstration. Finally, before I go to the demo, make sure I'm keeping track of time here. I'm not going to go into a lot of detail on other use cases for zTrustee, but just so you know, we can have other objects that you store in zTrustee besides zNcrypt keys. SSL certificates, SSH tokens for your cloud servers, other passwords, and anything else. And if anybody's interested, please contact Gazang, and we'd be happy to go over that information with you in this policy layer and other things we're able to do with those key objects. All right. So with that, let me jump over to my live demonstration. And what I have here, there we go. What I have here is a Couchbase node that I put together. I've got the Couchbase console is running over here, and you can see the current status of my server. I've got a couple data buckets. I'm using the really awesome beer sample data set that comes with Couchbase, so we can see things. I haven't been doing much on the server, but we can see the nodes and everything that's running and the overview. So what I'm going to be demonstrating here in just a minute is I'm going to stop Couchbase, encrypt the data, and then we'll come back and take a look at the server and make sure everything is still working and that we do have true, transparent data encryption. So over here on my server, Couchbase, as I said, Couchbase is currently running. I'll stop it in just a second in order to encrypt the data or do the move that we talked about. But before we do that, I want to talk a little bit more about the data at rest encryption rules that are allowing Couchbase to talk to my encrypted file system and preventing other things from doing that once I encrypt the data. Again, nothing is encrypted currently. So the way I do that is do a zNcrypt ACL, that's my access control rules, and then I'll do a list. And this command will show me all the ACL rules currently configured on my zNcrypt client here. So here's what I was talking about, the master key. A normal root administrator who does not know this master passphrase will not even be able to look at the ACL rules. So that's part of our security and that separation of duties that I mentioned. So I'll type in my master passphrase. If I get that right, I can hit enter. There we go. And I have 3 ACL rules that I had to put in place in order to allow Couchbase to function properly and be able to read and write to my encrypted file system. And so let's look at this first rule, and I'll kind of explain the rule structure, and then we'll go in and take a look at how this works. So all the rules are formatted like you see here. You see all 3 rules pretty much follow the same structure, and this would be the same, you know, for any process I wanted to do. Another example that you might consider is we have customers also encrypting web application files. Think of your web application that may contain authentication or user passwords for your back-end database or other resources. You could encrypt those and set up Apache as a trusted process. So there's a lot of flexibility here, as you can see in these rules. So the rule type is pretty self-explanatory. It's either an allow rule or a deny rule. Those are the 2 rule types that we have. Most of your rules will be allow, and what this means is that zNcrypt will allow this particular process defined here, and I'll get to that in just a second, to traverse that symbolic link and transparently read and write to the encrypted file system. So we're really allowing this to go through here. A deny rule, just for your information, would be for if I had encrypted a directory and maybe there was a subdirectory or a particular file that I wanted to omit from that encryption being able to be allowed to access by these trusted processes, I would have an allow rule like you see here at the parent directory level, and then a corresponding deny rule that would be applied at that subfile or subdirectory. That use case doesn't come up very often, but that's why we have that. So most rules will be allow. The next is the rule category. This is simply a tag or a label that identifies an ACL rule or a set of rules, and as you'll see in just a minute, it enables me to connect it to my encrypted data. So hold that thought, and I'll show you exactly where that connection comes into place. But as a preview, what this means is I can set up Couchbase rules and Apache rules all on the same server, and I can encrypt Couchbase data and link it to the Couchbase processes, and I can encrypt web Apache data and link it to the Apache process that I've defined. So that's the kind of flexibility we get here, and I would just name my Apache rules with a different category so that those could be identified separately. The path here, this is a scoping field for the rule. Most of the time you'll just do what I've done and have a wildcard. There is not a lot of reason to scope the rules because the scoping happens in the encryption or the move step that we're going to do next. Finally, the trusted processes themselves. And what I'm about to describe here for beam.smp is exactly the same for memcached and the i386 Linux go-to script or process that has also been defined here. So what we're doing, you'll notice I have the full path all the way to the executable or the script or the process or whatever it is that you want to be able to read and write here. And so we are uniquely identifying this known good process to allow it to read and write to my encrypted file system. So full path is part of it, as you see here. And then another piece of security that we do is we are going to fingerprint each one of these trusted processes or scripts that are listed here at the end of our path, and we fingerprint them with an SHA-256 hash. And what that does for us is helps us capture this known good version of the file, so that if an attacker were to try to get around all this by replacing your Beam and memcached and i386 Linux with their own evil versions of those same processes or applications or executables, zNcrypt won't allow that to happen because we have the fingerprint of the known good. If this is tampered with, we'll see that the fingerprint is different, and zNcrypt will actually stop that process that's been tampered with to going through and accessing the encrypted file system. So you have an extra level in addition to the encryption. You've got really a unique identification mechanism for your known good processes to keep those secure as well. We're not preventing them from being tampered with if somebody gains root access, but we will prevent the tampered program from accessing the encrypted files that zNcrypt controls. Now, a question somebody is probably asking is, well, what if I run yum update or something like that, or I upgrade Couchbase, then what happens? Well, in that case, you would just come in and run zNcrypt ACL --update, and this is the command that will resynchronize all your process fingerprints. So if you think any of these files were updated in a normal maintenance mode, you need to run update. Of course, I can only run it successfully if I know the master passphrase. So I type that in, and there, I just resynced my fingerprints on all those known good processes because maybe I just updated it. So that's how you handle that particular issue. All right, so that's a little bit about the ACL rules. One more thing I want to show you here real quick. Where's that file? Okay, this ACL.txt. How did I know what rules? I'm not a Couchbase expert, and I installed Couchbase a couple weeks ago and getting prepared for this webinar and to learn a few things about it, but I didn't really know what the Couchbase process was. So in zNcrypt, we actually capture unauthorized attempts to access the encrypted file systems inside dmessage. And this file here that I have, acl.txt, I captured the dmessage output in order to identify beam.smp and memcache and this i386 Linux Godo as my trusted processes. And so here's the output that I used to look at this. So here you can see that memcache was trying to access the data, and before it was a trusted process, zNcrypt was in place, and the action was a denied access. So not only did I use this to identify my good processes, this is where you can see if there have been unauthorized attempts to access your encrypted file system. So, and we log all, as you guys probably know, dmessage ends up in syslog, so we have a log of any unauthorized attempts to access the data. So we have a utility that uses this output from dmessage to generate the appropriate ACL rules. So anyway, just that's real quick on how I figured that out. All right. Let me, real quick, we're going to go look at the data in its unencrypted form. So if here as a root administrator, I can come into the file system here and be able to go look at the Couchbase data. So everything here I think is in opt Couchbase var lib Couchbase data, and you can see the listing here. Here's my beer sample, the data that I've been playing with inside the database. And so this is what I want to protect. I'm going to go ahead and stop my Couchbase server because, again, I am doing a zNcrypt move, as we talked about. So I'm going to go ahead and stop my node here. And once that's done, I'll show you where I'm going to be moving the data to. Part of my configuration, and like I told you on the slides, you would configure, let's say, var lib zNcrypt storage as your trusted, as your encrypted storage folder, and then the virtual mount point. So if I want to take a look at that, let me show you what we did. I can do a df, and that'll show me different mount points that I've got. And so here is var lib zNcrypt mount. So this is my virtual mount point, and it's an encrypt.fs. This is actually what's doing our encryption for us. You guys may be familiar. This is a crypto program that comes with Linux. It just doesn't have any access controls or key management, and so that's what we're doing. But anyway, this mount point is going to be my virtual, my symbolic link, and then var lib zNcrypt storage is the physical location of my encrypted file system. And you can set this up and put it wherever you want. So I've stopped Couchbase, and now I'm going to do the actual encryption command, and we'll see what that does, and I'll go over this with you, and then we'll go look at the data, and you'll see how it's protected after the encryption. So I'm going to do a sudo zNcrypt move, because I'm moving it from its original data directory into my encrypted file system. I'm going to do the encrypt option, and yes, there is a decrypt option. We can very easily, with a single command line, unencrypt all the data, put it back in its original spot, just like new, as if zNcrypt had never been here, if maybe we had to migrate to a new server or something like that. At Couchbase, here's how I'm connecting the rules to my encrypted data. Here's the data directory I'm going to encrypt, Couchbase data, and then I'm telling it which mount point I want to use. I can have more than one encrypted mount point and storage location if that was necessary for my server. So I'll go ahead and hit enter. Again, I must type the master passphrase to do this, and we'll go through, and it's telling me I'm moving my data from opt Couchbase var live Couchbase data, the original location, into var live zEncrypt mount, the virtual mount point, and then where we move the data. So with that now that it's been moved, let's go see what that really looks like. If I do a list like I did before, where we saw where our Couchbase data was, and I'm going to go up one level because I encrypted data, so let's look inside this Couchbase folder. You can see now that opt Couchbase var live Couchbase data is now a symbolic link pointing into my encrypted file system. So this is your first clue that the data is being protected. If I go back and try to concatenate through the symbolic link that 995.couch.1 that we did before, you'll see even as root, so this is the exact same command, so I'm trying to traverse that symbolic link here that data now is. I hit enter, and even as root, I get permission denied. So and the reason that happened is not because I'm root or not, but it's because concatenate is not a trusted process. I'm almost done here, guys. Got one more quick thing. Let me start back up Couchbase and show you that it's working, and then we'll see what questions we have. All right. And one other thing I'll show you too after we start this back up is I'll show you the encrypted file that now exists, where we moved the data to. So that 995.couch.1 is still a file on the file system. It's just moved into our new location, and I'll show you what that looks like, that we still cannot access it in that location either. All right, Couchbase is back up and running. If we come check our console, I refresh here real quick, log back in, and everything is working. All right, so we're there, and all our views are here, and we can see the performance, and I could go do all that. I'll do that in just a second if we still have a little time. But I want to show you the file now where it actually lives. So it's now been moved to var live zEncrypt storage, and then our directory that we encrypted. And here's my same beer sample file, 995couch.1. And if I hit enter and concatenate it here in the encrypted storage folder, you'll notice. Oh, hang on, sorry. Did I do that wrong? Let me see, I might have captured the wrong path here. All right, I'll pull this up. Let me navigate to it to show you guys. But with that, I'll turn it back over and let's answer any questions that anybody has while I'm doing this. So, Anil or Frank, I'll turn it back up to you.
Okay. Let me start with one question for Anil while you finish that process. So is the data encryption applicable irrespective of the bucket type?
Yes. So as you might know that we have two bucket types in Couchbase. So you can create a memcached bucket type and Couchbase bucket type. But with the memcached bucket type, which is only in memory, it doesn't come with the persistence. Whereas the Couchbase bucket type, it comes with both the in-memory as well as persistence. So the encryption is only on disk when the data is at rest. So so it's only for the Couchbase bucket.
Perfect. Thank you, Anil. I have a question for Robert from Patrick.
Sure.
Do you have some figures on how the performance will degrade with encryption turned on? And you mentioned that before, but I would like to reiterate this part.
The performance that we've seen, it's kind of a blanket performance hit of only about 2 to 5% additional overhead to handle that translation between the encrypted file system to a system that was not encrypted. So across the board, it's usually, as I said, those low single-digit measurements, and that's for CPU utilization, disk I/O, and latency is consistently what we see and what our customers see.
Perfect. Thank you, Robert. And another good question that we got still for you from Gordon. If you're starting from scratch, would you install zNcrypt before Couchbase and then not need to do zNcrypt move?
That's a great question. Yes, if you were that good at planning, and really not a whole lot of our customers are. Usually they come to us in a bit of a scramble. They finish their application and their data, and they need to do encryption. But yes, if you know you're going to be having this in place, you can avoid that initial time of the move, especially if it's large amounts of data. And you would still do the move, but before you put the Couchbase data in the node. So you would have to have Couchbase set up, have all the directories in place, do the move command on an empty database, and then however you import data into Couchbase, that would work seamlessly, and you would not have to ever do that initial encryption step all over again. So hopefully that is clear to you.
Great, thank you, Robert. Another question from Fujo. How much additional hard drive space will I need to store data encrypted?
Another good question. So the encrypted data is about the same size as the unencrypted data. In fact, the files original to encrypted are identical in size. There is a small 8K header that goes on to each encrypted file. So if you, and that's not much to worry about, I know, but if you wanted a precise difference in volume size, count the number of files times 8K, and that would be the extra space you need. Now, I did mention, I think I did, that initial move, it is a safe move. We do not delete the old files until we know the new encrypted data is in place properly. So potentially you do need that elbow room to handle the move. We do it on a file-by-file basis. So technically the elbow room you need is equal to the maximum or the largest file in your set, but you know, you do need a little elbow room, but after the move is done, the data is basically the same size.
Thank you, Robert. I want to make sure now you complete your part of the presentation before we move on to more questions.
Sure. Yeah, I'm having trouble getting down to my my beer sample file. It's here in this encrypted directory, but let's see what we get here. Okay, there we go.
Okay, yeah, there it is.
So there's the encrypted file. So let me capture this path. I think I just had the path wrong on my other command here. So I'm going to do and what I'm doing here is trying to get to the encrypted file, and I think I just had the path wrong in my attempt. But here is 995.couch.1, which is the one I've been concatenating. So let's see if this works this time. There we go. And so this is what I wanted to show you, is that in the encrypted file system, that same 995.couch.1 that I was able to concatenate before encryption in its original location, now if I try to get to it from the original location, I get permission denied, because concatenate or anything else I might run is not a trusted process. But if I find it here in the encrypted storage, which is now varlib zNcrypt storage and on down the rest of this path, the file is now fully encrypted. This is just garbled, useless information. So that's how we're protecting the data. You cannot get to it anymore from the file system perspective, only through those trusted processes in Couchbase. And that is the end of my demonstration. Thanks for your patience,
Great.
everybody.
Thank you, Robert. And we have 2 or 3 more minutes for more questions. We have a very interesting question from Manjunath, and I want to make sure we change the screen to Anil. So this is a question more about the roadmap of Couchbase. So, Anil, how the encryption will work for the in-memory data?
That's a very good question. So I would like to show you the roadmap of Couchbase. So in terms of security, we are heavily investing, heavily focusing on the security. And so from the last release, as I mentioned, we added the crime MD5 authentication in the current time frame, so the next release, which is our 2.5 release, will be adding a data encryption across the cross data center application. So if you have a cross data center application which is set up between the two data centers, the data which will be replicated from source cluster to the destination cluster will be encrypted now. And again, in 3.0 time frame, which is again a medium time frame, we will have the data encryption between the client SDKs and the server, and also the data encryption within the cluster. And beyond 3.0, we are focusing more on the user-based security, role-based security, and also the authentication support for LDAP and Kerberos for more secured authentication.
Perfect. Thank you, Anil. We have another question from Mark for Robert. How much downtime is required to move the data the first time you encrypt?
That's a great question and a very common question we get. So the way you would need to calculate that, my official answer is, well, it depends. But the way you can kind of figure that out to plan for it is if you know a rough amount of time it would take you just to simply move that amount of data, whatever it is. It really depends on the amount of data, how big it is. But however long it would take you to move that data from the one directory to another, and you would want to simulate if it's on separate volumes, if you've chosen to put your encrypted file system on a different volume, and things like that. But whatever that 1 gigabyte move may take in a normal move, for us, again, it's just our encryption sitting on top of that, add roughly 2 to about 5% of additional overhead. So if it took 8 minutes to move 1 gig, that may be really out of scale, but you get the idea. Maybe it would take 8 minutes plus about 5%, so 8 minutes and 30 seconds. So something like that would be how you could account for it. Roughly, it's going to take almost the same time it would take to move the data just in a normal move. Hope that helps.
Thank you, Robert. I know we are a little bit over time, but I want to ask 2 more questions. Sure. So one is, will the encryption keys be same across replicated Couchbase servers, and how much this encryption is going to impact the Couchbase performance?
Great question. So the encryption keys themselves are going to be unique on each individual server. That storage key that I told you about that we store on zTrustee, that's a randomly generated key, and it's randomly generated at each client. Because we're totally transparent from the local file system on the node up to Couchbase, any node-to-node communications does not depend on the underlying encryption matching or anything else. Couchbase will handle all the data transfer in between, and if some data goes from one node over to a different Couchbase node and is written to disk there, then the encryption happens during that write process on the other node. So hopefully that illustrates clearly the underlying encryption keys. They're all going to be different, but they don't have to be the same. Now that master passphrase, that key, it's up to you and your security policies. If you wanted to have ease of administration, make all your nodes have the same master passphrase. Or if you wanted to be more secure and make sure that if anybody did get their hands on one master passphrase, they couldn't get to everything, you might want to be more complicated and have a unique passphrase for every node. To me, that's pretty extreme, but sometimes security policies require that kind of extreme protection. The last question, back to performance. What's nice about it, that 2 to 5% overhead as a rough estimate that we see. I'm talking about that would be if you benchmarked one node operating on itself, one version encrypted and one not encrypted. Expand that out into a growing Couchbase environment where you're adding more and more nodes. Because we are on each node and the encryption is happening there, the performance maps out linearly. So typically we're seeing the same performance whether you're in a 3-node environment or a 100-node environment, because each node is handling its own encryption with its own 2 to 5% overhead. And that might magnify slightly, but we have not seen that in any of our benchmarking across large big data environments.
Thank you, Robert. We have a lot of questions coming in, but we have time for one last very good question. It's from Gordon. What happens if zTrustee isn't available due to weather or terrorist attacks?
Yeah, excellent question. So if zTrustee cannot be reached, The component of our process that is interfered with there is the automatic loading of the key back into memory, as I explained. So in that case, there still is another path where you can still bring your server up into functioning mode and get that key loaded into memory. We have one, I didn't tell you about this, but there is one more copy of that file level encryption key that is stored locally on the system. However, it's been encrypted with your master passphrase. So that master key encrypted the copy of the file key, and we do store that locally. That gives you the ability to run a DR command that says start up zNcrypt, prompt me for my passphrase, and then it will decrypt that key copy and load it into memory instead of the zTrustee key manager.
Perfect. Thank you, Robert, and thank you again for the awesome presentation. This is all the time we have for today. I want to remind everyone, if you have any further questions, please contact Anil at Couchbase or Robert at Gazang, and you can see their email address here on the slide. And thank you again for joining us today. I hope you find this useful, and I hope to see you again at the next webinar.
Thanks, everybody.